Hello everyone, welcome back to the linear algebra series, and today I'm going to be teaching you all linear independence and linear dependence. This might seem overwhelming at first, all this information, but I'm going to break it down for you so that it's easy. So let's just first see the definitions. So it's linear independent when no vector in the set can be written as a linear combination of the others. If you all are wondering what a linear combination is, please look back at my previous video where I explained this topic. So the only solution to the linear combination equation is the trivial solution, or all coefficients are zero. And linear dependent is when it can be written as a linear combination of the others. And there's a non-trivial solution where at least one coefficient is non-zero. Let me explain what these coefficients are and what it can be written as a linear combination means. So these are, this is the equation. So C1 V1 plus C2 V2 until how many ever set of vectors we have, that should be equal to 0. And this, and a set of vectors is linearly independent only if this equation, the solution of this equation is C1 is equal to C2, where it's equal to 0. That means all the C's, C1, C2, and all the way up till Cn are all 0. That's what it means here, where we say all coefficients are 0. So all the C's have to be 0, and they all have to be equal to each other, which is implied because they all are 0. And if not all Ci's are 0, then they're linearly dependent. So if we look back to the definitions, at least one coefficient is non-zero. That means that at least one is not 0. So not all Ci's are 0. So this is the definition, and it still might be unclear to you guys, but let me explain it with the help of an example. So if you all are firstly wondering what Rm is, I'll explain it right now. So the symbol R just denotes a set of real numbers, and let's just take R2 for example. R2, this means it's a two-dimensional Euclidean space, and in R2, a vector can be written as v1, comma v2, where v1 and v2 are both real numbers. And examples of vectors in R2 could be 1, comma 2, 0, comma 0, etc. So this is essentially what the Rm means. But in this case, it's Rm, so it's the real numbers of length m. So now let's go back to this question. So we have v1, which is 1, comma 2, and v2, which is 3, comma 4. So let's first check if they're linearly independent. To do that, we know that we have this equation C1 V1 plus C2 V2 should be equal to 0. Let's go back here. We're using this equation right here. So let's plug in V1. So C1 times 1, 2 plus C2 times 3, 4 is equal to 0. So now let's carry out the multiplication. That would give us C1 plus 3C2 plus 3C2, and the bottom part would be 2C1 plus 4C2. That should be equal to the 0 vector, which is 0, 0. So sorry, I should have written that here. It's 0, 0 as well. So now, if you're wondering how we got this and this, is just a simple matrix multiplication. So C1, you multiply to this term, and then C2 is multiplied to this term, and then you just add the top and then add the bottom. That's it. So now we have a system of equations. So now let's go about solving this. So we have C1 plus 3C2 is equal to 0, and then 2C1 plus 4C2 is equal to 0. So now we can solve this system of the system by, firstly, we can multiply the first equation by 2. That would give us 2c1 plus 6c2 is equal to 0. 0 times 2 is still 0. So now let's subtract second equation from this result. So 2c1 plus 6c2 minus 2c1 plus 4c2. That is equal to 0. So now I'm going to solve it right here. So the 2c1s get cancelled, and we're left with 6c2 minus 4c2 is equal to 0. So 2c2 is equal to 0. So that means c2 is equal to 0. And if c2 is equal to 0, c1 plus 3 times 0 is equal to 0. So c1 is also equal to 0. So now let's sum up our answer here. So we got c1 is 0 and c2 is also 0. And so therefore c1 is equal to c2, which is equal to 0. Let's go back up to our question, to the initial notes. We can clearly see right here that c1 should be equal to c2, which should be equal to 0. If this is the case, they're linearly independent. So that means that this set of vectors v1 and v2 are linearly independent. So these two vectors are linearly independent. Now let's look at another example. So in this example, let's consider three vectors this time to check if their vectors are linearly independent or linearly dependent. So we have u1 and u2, which is 2, 4, 6, and then u3, which is all ones. Okay, so now that we have these three sets of vectors, let's first check if they're linearly independent by setting up the equation c1 times u1, which is 1, 2, and 3. We're again just using the same equation, which we showed in the notes. C2 is 2, 4, and 6, and then finally C3 is 1, 1, and 1, and this should be equal to 0, 0, and 0. And if they are equal, they're linearly independent. So this gives us the system of equations C1 plus 2C2 plus C3 is equal to 0. That's our first equation, equation number 1. Our second equation is 2c2 plus 4c2, sorry, 2c1 plus 4c2 plus c3 is equal to 0. That is equation 2. And then finally, equation 3 is 3c1 plus 6c2 plus c3 is equal to 0. That is our equation number 3. So now we have these three system of equations. So you can notice that U2 even though we have these three system of equations, we know that if we have C1 is equal to 0, C2 is equal to 0, and C3 is equal to 0, the system of equations will hold true and they all will be equal. However, that is not the only solution. There can be other solutions to this. For example, C1 could be -2, C2 could be 1, and C3 could be 0. So for this solution set also, the system of equations holds true because let's try it for the first, for example. You'd have -2 plus 2 plus 0, that is 0. 2 times -2, which is -4, plus 4 plus 0. So this is also 0, and then -6 plus 6 plus 0. So you can clearly see that these three zeros are not the only possible solution set, as this system has infinitely many solutions. So you can notice that this is hence linearly dependent. Another way we can find out if this is linearly dependent is, let's go back to our original set of vectors. We have u1, u2, and u3. So what can we find anything common between these three vectors? We can clearly see that u1 and u2 have something in common. u2 is equal to 2 times u1. So if you multiply the first by 2, you get the first of u2, and so on. So 1 times 2 is 2, 2 times 2 is 4, and 3 times 2 is 6. So you can clearly see that u1 is just a multiple of u2. So since this is true, it means that u2 can be written as a linear combination of u1. u2 can be written as a linear combination of u1. So since it can be written as a linear combination, the whole set of vectors u1, u2, and u3, they're all linearly dependent. So these three vectors are linearly dependent. So to sum up what we learned today, we learned linear independence, I'm just going to write it as Li, and linear dependence, which is Ld. So when two vectors are linearly independent, it can be written as a linear combination of the others, and the only solution is when all coefficients, sorry, one second. Yeah. So the only solution is when all coefficients are zero. So in linear independence, all coefficients are zero, and no vector can be written as a linear combination of the others. However, when it's linearly dependent, at least one vector in the set can be written as a linear combination of others, and at least one coefficient is non-zero. So C1 or C2 or whichever C value is non-zero in linear dependence. So understanding linear independence is crucial in many areas of mathematics and its applications, such as solving system of linear equations, finding bases of vectors, and more. So this is a really important topic which you must know. I hope I was able to break it down for y'all today, and I hope y'all like and subscribe. It really helps me out a lot. So thank you so much.